Hello everyone. In my previous lectures I have completed up to the definitions of cancellation law, units and divisor of 0, and I have shown their interrelationships that if a particular element in a ring is a unit, then it can never be a divisor of 0, and also if cancellation law has to hold, then there is no presence of divisor of 0 for that element and vice versa. So therefore those were the interrelationships. Now I also took examples of the ring Z5 and Z6. In class also I have distinguished these two rings. I have told that although they belong to the same category of rings, that is Zn, but in Z5, in the lectures also I have given the examples that in Z5 all the non-zero elements are units, whereas in Z6 all non-zero elements are not units. The classes 2, class 2, class 3, class 4 in Z6 are divisors of 0, whereas classes 1 and 5 are units, whereas here classes 1 to 4 all are units. Now what makes the difference between the two structures? That is what we should be very careful about, and from here not only the result is important, but the problems in pertaining to the result are also important. What are the results, or what are the observations from these examples? That if Zn has a unit, then that particular class number must have a special property related to n, that is they should be co-prime. Whereas since 5 is itself a prime number, hence every non-zero element less than 5 is co-prime to 5, and hence all the elements here which are non-zero are its units. Now the result that comes from here is that in a ring Zn plus dot, of course class addition and class multiplication referred to as plus and dot, be careful, a non-zero element class m is a unit if and only if GCD of mn equals to 1. In many classes I have already discussed these proofs. Let me give the outline of the proof. Since everyone is having the master lecture handout with yourselves, so you can refer to it and you can get the notes from there. So I am just giving you the outline and the understanding of the proofs basically. So what is Zn plus dot? I have already told in the time I was discussing the examples that it is a commutative ring with unity. What is the unity element here? Class 1, right? Because any element you multiply with class 1, you generate the same class. So therefore it is a commutative ring with unity. Now let m plus be a unit. Of course it is a non-zero element. Non-zero means non-additive identity. Always be very careful about it. Whenever I am telling it is a non-zero element, it is always in the sense of rings, and when I am telling it is a zero element, it is always in the sense of rings. So zero element means identity element, and to be very precise, additive identity element, because multiplicative identity element does not exist for every ring. Maybe it is existing for Zn plus dot, but it does not exist for every arbitrary ring. So for every arbitrary ring with respect to the first binary operation, always the ring is a commutative group, and hence it has an existence of identity element with respect to the first binary operation, that is additive identity. I am specially hammering on this every time, that whenever I am telling non-zero element, that is it is not a zero element, means it is not an additive identity element. So it is not equal to class 0. Now if it is a unit, what is the definition of unit? That there exists another class, of course the members of Zn are class members, so any member of Zn such that M class dot U class equal to class 1. I am not taking the commutative portion because it is a commutative group, so writing U dot M dot is optional because this implies this commutative. So M dot this, applying the operation mu whole class equal to class 1. What does it imply? That these two classes are equal means what? What will that imply? In class I had defined it that this is equal to class 0 by simple addition operation of classes. So it is equal to 0 class means n divides mu minus 1. That means if n divides mu minus 1, that means mu is congruent to 1 modulo n. Right? So you can write this or you can write this, which implies mu minus 1 equals to nv also by divisibility or by congruence, anything. So this implies mu minus nv equals to 1, which implies GCD of mn equals to 1. Now you are always in practice of writing GCD of AB equals to 1 if AU plus BV equals to 1, so plus, but here it is minus. No need to worry. If n is replaced, minus n is replaced by another integer, say n prime, then it will give you the plus addition. It is just depending on the integer. So if it is a positive integer or a negative integer, you will just take the negative sign inside the integer. So hence GCD is 1. So we prove the one side of the proof is done. Conversely, if we go for the other side of the proof, then how will we prove it? Now M bar be an element. So what I am telling that let M bar belongs to Zn and GCD of Mn equals to 1. So I am assuming this side and I will prove the other side. So for the other side I have to take M bar to be an element in Zn and GCD of Mn equals to 1. What will I prove? M bar is a unit, right? So GCD of Mn 1, what does it imply? Mu plus Nv equals to 1. So what does this imply? Mu minus 1 equals to minus Nv. That implies n divides mu minus 1. If m divides mu minus 1, that means mu is congruent to 1 modulo n. Right? Up to this it is clear, I think. So now, of course, u cannot be 0. U cannot be 0. It has to be a non-zero positive integer. It is always a non-zero integer. So if it is an integer which is a non-zero integer, then because by this only you can generate that u is non-zero. So if u is non-zero, u has two options. Either this u is less than n or this u is greater than n. Now why am I telling this? In class also I had defined this, that if this is congruent to 1 modulo n, what does this imply? Like previous, here also mu was congruent to 1 modulo n. What does that imply? Mu minus 1 equals to nv or n divides mu minus 1. What does it imply? That this class is equal to 0 class because it is a member of Zn. So here also it will imply that mu minus 1 class equal to 0 class. So from there we can straight away get mu equals to 1 class. From there we can get m class u class equal to class 1. But here I cannot say m is a unit. Why I cannot say m is a unit? Because in u class, this u class, I do not know whether I can write it as a class. Because if it has to be written as a class, then its members should be present in Zn. U should belong to Zn. So if u belongs to Zn, I have to prove that u is less than n. Otherwise u cannot belong to Zn. I have only proved up to here that u is non-zero, but I haven't proved that u must be less than n. So this is still in question. So how can I prove that u is less than n? Let us take the contrary, that let u be greater than n. if u is greater than n, I can divide u by n. So I can apply division algorithm. So if I apply division algorithm, I can write u equals to nq plus r. R is the remainder. So what is the definition of r? 0 less equal to r less equal to n. Now from here I can write nq equals to u minus r. From here I can write nq equals to u minus r. What does that mean? N divides u minus r. What does that mean? U is congruent to r modulo n. Why have I written it? By the same logic. This divides this means n, u minus r is divisible by n. That means u minus r whole class is a class which is divisible by n. That means it is equal to 0 class. So from here I am reaching this conclusion that u is congruent to r modulo n. Now since u is congruent to its remainder class, now I can say that therefore u class equal to r class, right? U class equal to r class, because u minus r is divisible by n. So u minus r class is 0 class. So u class equal to r class. So what is the speciality of these classes? That these are remainder classes. So they are not greater than n. So they are always less than n. So I can reduce any greater than n class to a less than n class by converting it into its remainder class, because this is true, by applying division algorithm. So now I can say that each m class dot u class means m class dot r class means class 1. I had stopped here, no? M class dot u class, I was not telling m is a unit, because u I don't know if it is less than n. Now I can write any u class is equal to r class, and hence I can write this. So now I can say m class dot r class equal to class 1. So I can say m is a unit. That was my intention of the proof. So hence the proof.